I can't look at you.
Ah, all right. That is your result. So there you go. Move around.
Hannah! He's still sick. Oh my gosh.
No rhyme or reason to it. I just move people around, so if you're in the same spot, really sorry. No rhyme or reason to it.
Dang, I moved too far. Ben? So sad.
Did I forget anybody? Yeah, are you on there? Here's on there twice.
Like this.
Put me on there twice. With Michaela's mom.
No, because we have to do some of the back lesson.
Oh, alright. Sorry.
There's one
Alright. Perfect. Okay, everyone's found their spot. Perfect. Alright. Okay, alright. Here's what we're going to do today. We're going to do a few notes, then I'll give you a little bit of time if you need it to work on your assignment today. I think most people kind of wrapped it up yesterday. I just want to go through a couple things. I thought PowerPoint was probably the easiest way to cover it because we're just doing a bunch of vocabulary terms today. Nothing really in-depth, nothing difficult. Just we do need to get through a couple notes here. So, homework, page 111. Remember that's due tomorrow. Just keep that in mind. End of the quarter is tomorrow. So if you have any late work, anything that's missing in the grade book, that type of thing, those are due tomorrow by the end of the day. I'll be here as long as you need me to, but if you're going to redo something, so I handed back some homework yesterday, redo it. Fix the mistakes, turn it back in, that type of thing. Or if you notice, like, I handed it back to you, it was graded, but it's not in the grade book, turn it back in. That was one of the things I warned you of. I think there was only a select few people that I did not turn homework back to yesterday, because you were gone. So, or you turned it in late, so. Only a select few here, so I think like Sokol, you were gone. Who else was gone? Ryan was gone. Max, you were gone. So there you go. So I'll hand some of those out. Okay, but let's go through just a couple notes here. Pretty straightforward, pretty easy. But again, check your grade today. Check JMC, see what you're missing. If there's like a late LI in there, that means it's missing. Get it turned in to grade. Okay, this is our topic today, postulates and proofs. It's our first day where we're really formally introducing postulates, properties in geometry. Postulates are something we will discuss. There's a lot throughout the chapters. I can think back to last year. I think overall there was like 17 different postulates throughout the entire year. I'll explain what that word means here in a minute. These are ones that we can use to like prove stuff, especially when we get into like those more difficult problems where you can look for properties and something. Proofs, we'll get to that as well, but this is our main topic here. So let's give you a kind of outline of our goals today. So number one, I'm going to talk about the law of detachment. That's something that your book refers to in the beginning of this section to talk about how to do proofs. So I'll discuss that. I'll do an example of that. We're going to talk about the law of syllogism. So that's, again, another way of proving things. So we'll do an example of that. And I will really discuss like what these look like. How does this law differ from the first one? How does the look work? And they're based on deductive reasoning, not inductive. So I'll explain the differences there. We'll talk about postulate. We'll actually define that word today, or an axiom. Some textbooks refer to it as an axiom. That's a really old textbooks. And then once we're through that, then we have a bunch of postulates to get through. We have 7 today that I want to get through, if possible. I do want to give some think we're out of here at what, 10:02 or something like that today? Yeah, 10:02. So, all right. All right. Then we're going to hit our first theorem. Theorems are different than postulates, and I'll explain the differences. I'll go through the definitions, so you kind of know why. And we're only going to do our first one today, the first theorem, which actually has a name. Usually theorems have names. Some postulates do, some don't, but theorems usually do. Okay. Any questions with what we're going to do today? Okay, it's pretty quick. Again, I'll put this PowerPoint online. I'll put it on my website probably tomorrow morning, just so you can kind of look at it. I don't think I posted yesterday's lecture on because it was just basically a work day. So, all right. But again, theorems go with proofs, so that's a big deal. So that's kind of our goal today is to talk about how to prove this and why we have that. Okay, so law of detachment. Let's do this one first. Law of detachment, if you want to know, it's using deductive reasoning. So deductive is like how you memorize things, right? Memorizing rules, facts, definitions, properties, postulates, theorems, that type of thing, formulas, to prove something, okay? You're trying to, the goal in that, the law of detachment is trying to get to a valid argument, to get to a valid proof, like proving a conjecture, that type of thing. We'll get to that word later. But I want to give you an example, like what law of detachment looks like for like a math problem. So, if P then Q, that's a true statement. Let's assume that it's true, but we have to somehow show it or use it, right? So again, how this statement's true, the first part has to be true and the second part has to be true. That's what makes the statement true. It's kind of like a conjunction, right? The and, true, that type of thing. Now, how this works, to give you a sentence for how law of detachment works and how deductive reasoning works. So imagine that you had your bank account is empty and you're not able to purchase something, right? So if your bank account is empty, then you'll not be able to purchase something. So there's money, right? So you don't have any. So what would you say if my bank account was empty? What's the logical argument you can say if my bank account is empty? Just knowing this fact. Yeah, exactly. Then I'm not able to purchase something. What you just did there, just saying like I'm not able to purchase something. That's the law of detachment. Applying a single sentence to something else, like a different sentence completely. But you can see that they had the same setup, right? My bank account is empty, so then you're not able to purchase something. That type of thing. That's detachment. I didn't say anything after this, right? I just said my bank account is empty. So you guys made that logical step, the deductive part where you said this. That's using deductive reasoning. It's memorizing the first sentence and using that same reasoning for the second. That's law of detachment. You're detaching the end part and attaching it to the end of my sentence. Does that make sense now? That's law of detachment. It only takes deductive reasoning. Okay? So it's justifying something. I think the book refers to like in a restaurant menu. Things that have a star next to the items are signature dishes that the restaurant serves. So, and then it says, like in the next sentence, Stephen recognizes one of the dishes has a star. So then what does that mean? Well, that means that's a signature dish. That's a law of detachment. Just being able to apply common sense stuff to later on. We use this in math all the time. You know, one of the things is, like when I started using this for the first time, okay, you guys started to realize after a while what that meant. So what do we use this for? Like what's that symbol for? What does it mean? Line signal, right? We apply that to a lot of different things, right? But just being able to apply this to later objects, like later items in the chapters, you're detaching it. You're doing law of detachment. You're using deductive reasoning, memorizing something that I taught you and applying it later. That's what that is. That's a way of like proving something. I require that you have to have some formal deductive reasoning in this class. You have to be able to at least remember some things and apply them later to make a proof. So certain things I want you to memorize in this class. I want you to memorize theorems when we get them. Certain postulates when we get them. Certain ones, not all of them, because obviously we're doing about 7 today. But there's certain ones I do want you to memorize, especially the ones like names. They're important enough to have a name for me to use them later. That type of thing. All right. Any questions with the law of detachment? It's kind of a way of proving things. Remembering something and then using it later. Okay, that is different than the law of syllogism. I think I'm pronouncing it syllogism. The law of syllogism, again, it's deductive reasoning, so you've got to memorize something and then you've got to make a valid argument using it. But the example I want to talk about is, what's the best way I can say it? It's a transitive property. Maybe that doesn't explain it to you. A transitive property is when you use if, and then. It's like, it's putting together 3 items in a row. Okay, so let me give you an example here. So, if then, and if Q then R. So if P then Q, and if Q then R. So the idea is that there's a string of items happening here. Something happened that caused this. If this happens, then it causes this. The best way I can put it in terms of technology is for you guys. It's the app, if this then that, right? It's an app you can get in an app store, you can get it on your Mac or Chromebook or whatever. But all it does is it does a string of arguments for whatever the app. You can set it up to do anything you want. So most iPhones use it in the background, this program, if then that. How that works is on your phone, you can set a reminder when you get to a certain location. That's something you can do. A lot of people don't realize you can do that in the menus of your iPhone. That you can set reminders like buy milk when you're at a certain geo placement on the globe. So when you start driving to Target and you get in the parking lot, it'll remind you to buy milk on your phone. It'll chime at you and it'll show it on the screen. That's a law of syllogism, right? It's applying knowledge that you set a reminder for this certain location, so that when you showed up at the location, it reminded you of it. It did something, right? That's a true statement. All the parts have to be true. P is true, Q is true, then R is true. Okay, so the example for geometry that I would use is if you have a square, then you have a rectangle, right? Because a square is a rectangle. So here's a square. It's a rectangle. It fits the same definition, right? It's 4 walls, it's got right angles. So if you have a square, you automatically have a rectangle. Well, if you have a rectangle, what is a rectangle also known as? Quad or parallelogram. You're absolutely right. I could use either one. I think I used a parallelogram on this slide. So it's a parallelogram. I could have used quad there because it fits the bill. So if I have a square, it's automatically a rectangle, and it's automatically a parallelogram. So what's the logical statement? If I told you you have a square, what can you jump to? Parallelogram or quad, if you want to call it. Okay? That's a logical statement. You just did the law of syllogism. You're associating a square with the other shapes. You're connecting dots as you go. That's what you need to realize. So that's a valid argument. If you have a square, you automatically have a parallelogram. So here's the argument that I always use from year to year. Trish, how old are you right now? 15? Sadie, how old are you? Okay, so if I said Trish and Sadie are the same age, and Trish is 15, so how old is Sadie? 15. You guys connected the dots, right? Unless you heard me talk, right? So if I told you they're the same age, she's 15, then you automatically, in your head, you associate she's got to be 15. That's a law of syllogism. You're connecting dots even though you don't have to say that. That's the idea. That's something you need to realize. Something that's really big. When we start, I think it's chapter 4, I believe. When we get to chapter 4, we start talking about these shapes. These shapes in particular, quads and other shapes. And we start learning properties about this one. What you need to realize, if we start learning properties about a parallelogram, it automatically trickles down the waterfall to these. Because these are the same shapes. They're parallelograms. So the properties are associated with the other ones. That's a law of syllogism. You're remembering things, it's deductive, but then you're also applying to something that I didn't tell you about. You just knew that these are connected. That's the idea. Okay? That takes skill. You need the law of detachment and the law of syllogism to like apply everything you remember. You remember things, you can recall them, but then you can also connect dots when I don't say things. That's the idea. Okay, does that make sense? Okay, I thought this was just an interesting topic to bring up because we're going to need this when we get into like really difficult math proofs, like really crazy difficult math proofs. And you start having to remember back to properties we've talked about and to reasonings we've discussed and using the same style to do proofs. So that's what we're doing. Okay? All right, I just thought this was interesting enough I want to bring it up. All right. Okay, so let's talk about the first thing. Let's talk about these postulates and what we're going to be going into. So the idea of a postulate, an axiom in math. It's a mathematical statement. Okay? That's all it is. It's a math statement. But the thing is about a postulate, we accept it to be truth. It's automatically truth. We don't need to prove it. We don't need to justify it. It's just truth. Okay, so something that we take for granted. Now, if I can like give you some basis on math. Would you agree with that statement? 1 plus 1 is equal to 2. That's a postulate in math. It's called addition. We consider addition to be a postulate, an axiom, something we take for granted. It's like a basis of all mathematics. That's what a postulate is, right? We start with something so basic that you cannot, like, there's no argument needed. It's just like a duh that has to work. And that's postulates. Now, you're probably wondering, well, if they're so simple, why do we have to state them? Sometimes they state the obvious. It's like hindsight, if you've ever heard that term in psychology. Hindsight's something that you know is like so common sense, but unless somebody said it, you would never have thought about it. Okay, that's a postulate, right? So it's some basis for mathematics. Axiom has the exact same definition. It's just this is a term that we've used in like previous old textbooks. One of the most famous axioms I can think of is a paradox. I think they called it like Achilles' paradox. It's just something we take for granted, right? And it's this weird axiom in math. It's so hard to prove because it's like common sense. So here's the axiom. This is Achilles' axiom, or this is why I've heard it referred to as a different axiom. But imagine you had Achilles is chasing Hector, right? Like in around the city of Troy, right? So here's Achilles. He's chasing Hector. All right, there he is. All right, and he's chasing him. And every time they make a lap around the city, Achilles cuts his distance down by half. So every time they make one lap around the city, his distance now is cut in half. So that's the first lap. Will Achilles eventually catch Hector? Okay, say it. No. In theory, mathematically, no. All right. If he's always cutting his distance down by half, he'll always have some space in between them. He'll always be halfway closer. But what does common sense tell you? Will he eventually be able to touch him, like physically touch him? Yeah. Like it's this weird axiom. It's so hard to prove both topics. I can understand both at the same time. If you're cutting your distance down by half, there's always some like molecular distance between them that they're not touching. It's just they're halfway closer now. But common sense tells you that yeah, he'll eventually be able to grab. He's so close, he's just right there, you can bear hug him, right? So that's an axiom. We just take it for granted that if he's cutting his distance down by half, eventually we will be able to touch him, right? But mathematically, no. It's this weird thing. It's like this little catch. Postulates, we just take for granted. It's something so simple. It's true. Okay? All right. So let's talk about this next postulate. This first is actually the first postulate in our textbook. Okay, so here's what it says. Through any 2 points, 2 dots, there's exactly one line drawn through them. So any 2 points. So here's my picture. So I have 2 points, P and R, and I drew a line through them. We call that line N. That's a postulate. Now you're probably wondering, okay, why is that a postulate? It's literally like the definition of a line. You have 2 points, there's one line drawn towards them. But we have to state that you can actually physically draw it. Okay, now, what are the different names I could call this line? Line N, PR, or RP with the little arrows above it. Don't call it PN. It's not PN, it's PR or RP. Okay, N is not an actual point, it's just the name of the line, so we just call it line N. Okay, so this is the shape, right? That's postulate 1. Any questions, comments, concerns? Easy, right? It's common sense. We're going to do the same thing for a plane. So if there are any 3 points, non-collinear, there's one plane. So there's your plane. You have 3 non-collinear points. There's one plane touching all 3 of them. Only one when they're non-collinear. So on this particular picture, these 3 dots are on my marker board. So this is the plane that touches them. Plane K, or you call that plane ABC, or plane CBA, or plane BCA. You can do any combination. Planes can be in any order. But they have to be non-collinear. If they're in a straight line, there's an infinite number of planes that touch them. Because you could tilt the plane at different angles and it would hit all 3 if they're in a straight line with each other. I'll show you a picture later what I mean by that. If you put the 3 in a straight line, you could have multiple planes touching the same line, or the same point. Okay. Questions on the first 2. They really just go back to definitions. Now we're going to reverse this. So I started with, if you start with points, you can draw a plane connecting them. Now I'm going to start with the plane and go the other direction. So if you have a line, now you have to have at least 2 points on it when you draw it. You can't just draw a line with 1. You have to have at least 2. And the word at least means a minimum. So in that picture, I gave you 3. So what can I name this line? What are the different names? N, line N, or PQ. I use two letters. Or line QR, or line PR, or line RQ, or line RP. You can have any combination, but you can't use 3 letters. You use 2 letters. 2 points. So that's a line. Okay, and then we go the other direction for, if I was thinking back to the postulate 2-2, right? That was the one where it says if you have 3 non-collinear points, you have a plane. Well, now we're going to reverse that for 2-4. I'm going to give you the plane. There has to be 3 points on it. So if you start with the plane, you have to have at least 3 non-collinear points on it somewhere. So on this picture, I have 4. Minimum of 3. Okay, are we good with the first 4? They're common sense. If you don't know, they're converses of each other. If I give you this sentence, literally postulate 2-2 is the converse of it. You switch it around. If there are 3 non-collinear points, then there's at least 1 point. Okay, now, what my next couple of postulates are going to be, because I said we're 7, we're going to start interacting these objects, crossing them, touching, that type of thing, and that's where the next few postulates. So this is where the basis of all geometry comes from, like how we make a point, how do we make a line, how do you make a plane, that type of thing. Okay, so here we go. So let's talk about the intersection, right? So 2-5, 2 points line a plane. Oh yeah, I forgot about this one. If 2 lines line a plane, so I'm gonna put the plane here, and I'll put 2 points on it. Then the line that touches them, that contains them, is also on the plane. That right there is like the very definition of duh. Right? You have 2 points on my flat surface, my marker board. There's a line connecting them. So then that means that line also has to be on the plane itself. It can't be just magically bridged off of it. Forgot all about that. They put all 3 together. Okay. Are we good with everything so far? Pretty straightforward. This one is the one where it associates line with plane. All right, so now the intersections, right? So the first one I'm going to start with is 2 lines intersecting. So this is postulate 2-6. When 2 lines intersect, they form exactly 1 point. So here you go. 2 lines cross, so line S, line T, they formed a point in the middle. That's how you get points. 2 lines crossing. lines intersect exactly 1 point. The best way I can describe this, so imagine you have 2 laser pointers back up here, and you're to point them exactly at each other, like one's pointing this way, one's pointing the other, so they're intersecting. They'll literally make a dot in the middle where they cross each other. Like where the 2 beams actually hit will actually make a bright point right there. And that's what's happening here. If I had 2, I could show you that. Okay? Alright. Now, the other, so 2.7, my last postulate, is where we intersect planes now, not lines, but planes. Now when planes cross, what do they form? So if I had a flat piece of bread and I took another knife, a butter knife, and that's a plane, and I cross them, what do they make on the bread? A line, right? So here's the idea. So 2 planes cross, they make a line. This is exactly the picture I wanted to show you earlier. That, I think it was postulate 2.2, the one if you look back and you're looking at, if you put 3 non-collinear points down, it makes a plane, right? But if you put them in a straight line, so if I had 3 points on this black line through line W, you could have an infinite number of planes that touch them. Like if you had 3 points in a row. That's why they had to be very specific, non-collinear. Because if the 3 points in a row, do you see how I have multiple planes that can touch the line? So when you put them non-collinear, it makes one individual plane. But what this postulate is saying is that when you cross them, like, so here's my piece of bread, here's my knife, and I'm cutting through it, it's making a line in the bread. Perfect line from top to bottom. All right, questions, comments, concerns with postulates. A lot of these postulates are just basic truths because they literally are definitions. But some of these are just like things we just obviously need to talk about. Okay, so now, we've done postulates. We don't prove postulates. We assume they're true, so we can use these later. Let's talk about theorems now. We only have 2 slides left. This one and then. Okay, so theorem is a mathematical statement or conjecture, and I'll explain that word conjecture. So I've used that word a couple times now. That we need to prove to be true. It needs to be proven. Okay? This is something that is maybe not obvious. Maybe it is. But we still need to show why it works. It's not as simple as just a definition. So it's got to be some reason. Now, the first theorem is questionable. It's used in every textbook. I always question whether it's a theorem or a postulate. But every textbook says it's a theorem, so I'll state it here. But again, we have to prove them. Now, let's talk about this word conjecture. Conjecture, if you don't know, it's a statement. It's a reason. It's a conclusion. But it's made using inductive reasoning. Inductive is noticing patterns to make statements. So it's a statement or it's some pattern that you've noticed in nature that's been happening recently. And what you're going to try to do is you're going to try to prove that it's true every time at that point. So that's conjecture. So it's one or the other. It doesn't matter. All right, but again, proof. Like if we're going to try to prove it, it's using some method of showing why it's true. Okay, so it's proving that statement or conjecture. That's what a proof is. That's what we do in geometry a lot of the time. You always hear people complain about proofs. It's not bad. And when they get out of here, they always think it's not as bad as they always thought it was. And when you get to the upper level math, these are the least of your concerns. Okay, so let's talk about this idea of proof. How do you prove something? So there's different methods. Number one, there's something called a paragraph proof or informal proofs. That's where you write down in a paragraph your explanation of why this works. So you're stating properties, you're stating other reasons. Most people try to do that when they try to justify something. Oh, this is why it works because this. You're doing informal. You're stating things. There is a statement reason proof where you actually write all the mathematical statements and all the reasons why they work. So like properties, theorems, postulates, why something works. So you're actually giving a statement and the reason for that statement. And you go until you finish it. And then the last one, and this one is by far the hardest, is called an indirect proof. We'll see those later. Those will come up when we start using parallel lines. Those come up in later sections. We'll start looking at indirect proofs. These are the hardest by far to prove, because it takes so much logic for people to understand this. Okay, so these are the methods that we're going to learn this year. The one that I basically use, like, without a doubt, is statement reason. That's when we do, like, the most in here. There's some times that there's no purpose for doing this, and we'll just do a paragraph. We'll just talk about it. Sometimes, like in those parallel line problems, we'll start doing indirect, which are the hardest. But it's just proving a statement. First theorem of the day. This one's easy. Okay? M is the midpoint of AB. So M is the midpoint of this segment. What we're going to try to show is that the two sticks have to be equal to each other. So here's your picture. And yes, we have to prove it, which is silly. This is the one that I don't agree with, that I think is so common sense. I don't know why we prove it. Okay, so let's talk about this. How do we do a geometry style proof? The first part we have to do is we have to write, we're going to do a statement reason. It's kind of the way that I like to do it. Statement reason. So statements are going to be over here. The first line of the statement is we start with what's given to us. The last line of the proof should be what we're trying to prove. This is the last line. However many lines it takes me, whatever the last line is, it should be this. At the very end, I want to end with AM is eventually congruent to is equal to MB. The two sticks are equal, and then there has to be a reason for it. Right? So something was down to that point. Okay, so that's a statement of reason. Now, line one is always the simplest. You start with, what did they give you? What did the first line state? Say it? Yeah. M is the midpoint. Midpoint of segment AB. And the reason why this works, it's literally the given. They gave us that information. That was true on that picture. M is the middle. Okay, M is the middle. Line 2. Now we usually on this step, we state something obvious maybe from that definition, or we state something obvious from the picture. I'm going to go off the definition. Definition of midpoint, according to your math book, that M is the middle, and then the distance, the length of AM. This is how you write distance. You write AM, the segment, but you don't put the little bar above it. You don't put the bar above it. You leave the bar off of it. That's the length of AM has to be equal to the length of MB. They're exactly the same length. The reason why this works, that is the definition of midpoint. That the two sticks are exactly the same length. So if you go back in your book, you'll actually see that. If you go back to midpoint, that was the first chapter we did. We talked about midpoints. The two sticks are the same length. So that's how you write it. So now, if the two sticks are the same length, it means their measure is the same. Does the pictures look the same? Yeah, so that's size and shape, right? So they have the same size and shape to it. They're proportional to each other. So if they have the same size, shape, and measure now, because this is covered measure, what can you tell me about the two segments now? They have the same size, shape, and measure. They're equal to congruent, which is exactly what we're trying to prove. Line 3, since they have the same size, shape, and measure, we can say that the segment AM is congruent to the segment NB. They're congruent to each other because they fit the definition of congruent. I know this is your first time seeing a proof. This one's silly. I know it is. It's so simplistic. Like people would think, oh, well, duh. But you have to prove it. You have to show that the two sticks are the same. And we have to fall back to a formal definition. That the sticks are the same length, so that means they're congruent to each other by definition. Okay. Questions, comments, concerns. That's what you're just looking at. This is a proof. This is what we're going to be doing in this class. And you would have to do these at some point. it'll make more sense when we get there. This is your first view of it. The ones we will usually do, we'll do a lot of algebra proofs. We just do some math. Proves why something works. Okay. Homework today, or the one that's due on Friday, due tomorrow, is page 111, 1 through 8, 10 through 17. You have the rest of the time of the day to work. That's not a lot. I'm sorry. It's due tomorrow. Remember that. All right. Now I need to hand up some papers. So if you need to move around, you can. If you already got 111 done, you can turn it in. It's not a big deal. All right. I need to hand out some papers here. So Trinity, here you go. Here's the paper. This one that you turned in yesterday. Right in there. Okay. Hannah, here's one that you turned in yesterday. Great. Rachel, did you sit right here? Max still gone? Ryan. Still gone. Max. Still gone. Rachel, here you go. Cold paper, that.
Yeah, we can do it. I have money in my house. Yeah, I think it's I'm gonna be hungry, so yeah, we can.
Two more sentences.
I have like one more somewhere.
Only one paragraph. Oh yeah, I hear that closing your grade.
Okay, remember, check your grade online, see if you're missing something, and if you are, you should probably get that turned in before tomorrow, so I can get it graded. I'll go through the list of who owes me something right now. People that owe me something. Michaela, you still owe me 2. Ben, you owe me 2. And Ryan, thanks. So there you go. So if you need a printout, I can do that. But make sure you're checking your grades. See what assignments you're missing. Turn them in.